and good evening, and welcome to Codebase Alpha, episode 71. Now, before we get too much into the episode, I'd just like anyone who's out there in the chat. Then, could you just give me an indication about the audio? Because last time out we had quite a few audio problems initially with the show, so it'd be great if someone could give me a report about what the audio sounds like. It was clipping out and also very quiet last time. I'm hoping that I've sorted that out, but it's very difficult to tell. So if someone could give me a quick report on audio levels for my voice, that'd be fantastic. Let's go and put some music on. Cody Beard, thank you very much for that report. Audio's okay. Musical Bookworm, oh, welcome to the stream. Not seen you before. Welcome to the stream. Thank you for the report. Audio's okay. That's good. So let's have some background music as well. If that's too loud, do let me know. This is a bit of Relax Daily. We've only got 3 tracks, so it's going to be quite repetitive, but I don't actually listen to the music. It's just something there to help kind of focus, really. But yeah, if you're interested in Relax Daily, relaxdaily.net, there's hundreds of tracks on there, which unfortunately you have to pay for. But these 3 tracks that I play on the stream, they're free tracks and also licensed to people to use on streams and YouTube and things like that. So there's a kind of advert for Relax Daily. So we're going to play some of that. I've actually been listening to a bit of Tangerine Dream, do my coding at work today, so that's been quite interesting. Very sublime stuff. Okay, so we're planning to do some more shader streams soon. Unfortunately, both Morton and I have been very, very busy at work, and we haven't been able to kind of link up and organise the next shader stream. So Musical Bookworm, you say you haven't been able to catch one of my streams before. You watched some of the videos, so thank you very much for watching those. If you haven't subscribed to the YouTube channel, please do so. We're kind of chasing 150 subscriptions on there at the moment, and we had a really big day. I think it was on Friday. We had a big jump in the number of subscribers. Thank you for the follow, Musical Bookworm. Unfortunately, we don't get the follow alert on this particular scene, but when we switch over to the coding screen, I'll give you some hype there. As I say, we had a big jump in the subscriptions on YouTube on Friday, and also on Twitter. So if you haven't followed me on Twitter as well, do so there. I'll just pop my YouTube, and here's my Twitter. Into chat, so do follow that. Okay, so let's go over to the code and see what we're going to do today. So let's pass it into coding. So here we are. So for the follow, thank you very much, Musical Bookworm, for the follow. Have some Electric Elf hype. So this is one of our WebGL shaders. This shader was created by a friend of the stream, Pure Stable, aka Martin, who does actually be part of kind of the stream through the shader streams and also some of the stuff we've done together. And he's having a bit of a break in the last couple of weeks. So let's get down to business. So what we're doing, we're working on this Z80 emulator. We've got an awful lot of work to do on it. Mainly we're just adding opcodes at the moment, so it's quite a long, tedious process. There are lots and lots of opcodes to do, so what I'm doing is working on a lot of those off stream and then just trying to get some of the kind of more interesting ones to do on stream. So I and also the intention is to try and get a minimum number of opcodes where we can write a program which actually does something interesting in assembly language. So that's kind of where we're working towards. Eventually we're going to have a fully emulated CPU, and we're going to be able to write programs, obviously in assembly language, but we're also going to have to test it to make sure that it's accurate. But as we go along, we're using kind of a test-driven approach, a mindset, rather than a rigid methodology. We currently have how many? We've got 206 individual tests written. We write the tests ahead of time and then make them work. And we also use them as our kind of a red-green refactor step. So we've got that, but we've also got a whole bunch of tests here. So these fuse tests, which are kind of pre-written tests that have been used on an emulator for the Spectrum, in fact, which is another Z80 based machine. The free Unix Spectrum emulator is Fuse, and they've got about 1,300 validation tests by instruction. So this is instruction 0, which is no operation, instruction 1, instruction 2, etc. And we're going to have to write some code to run these tests and then report back any failures. It's a bit premature to run them just yet, because obviously there's many operations that we haven't written, so it would actually fail. But that's one of our objectives, is that we're going to have a good solid emulation, including the undocumented features of the Z80, which of course now have been documented, and then we're going to package it up as a NuGet package, and then it's going to be up on NuGet or on the GitHub package repository, so that people can download it and they'll have an emulator for a Z80 to do with what they will. What we'll do with it, it's yet to be determined, but we'll probably emulate some kind of retro computing device, an Amstrad CPC or something along those lines, and that should be interesting in its own right. And then we'll try and get something like CPM, the operating system, running on that, but it's going to be quite a long-term project. So we need to actually build all the operations that Z80 was capable of, and it was capable of many hundreds. Notice it's an 8-bit processor, so you'd think it's only maximum of 256 commands that it could run, but in fact they actually expanded that by having multi-byte operations. And in fact, the very latest version of the ZX Spectrum, the ZX Spectrum Next, which is coming out, well, at some point, hopefully, well, people are saying by Christmas, but hopefully by Christmas or in the new year, that has an enhanced Z80 processor in it, which has got even more operations. It's even got a multiply command, which the Z80 we're modeling doesn't have. So we may actually, once we can figure out exactly how that, the specs of that enhanced Z80, we may add those operations as well. But at the moment, I'm sticking to kind of tried and trusted and well documented Z80 operations, and it's going to be a classic Zilog Z80 rather than the other kind of variants on the Z80 that got produced. The hardest bit about it is actually the undocumented features. And luckily, there's a fair amount of information out there on the internet to help with that, and that's where the validation tests come in, because I can write tests using XUnit, but it's not necessarily going to. I'm not necessarily going to know exactly what the undocumented features actually do in every single case. I can try and find out, but it's quite difficult to know. Other people have been down that path already, and I can test my emulation against their tests. That's what that fuse test thing is going to be all about. Okay, so one thing I want to quickly test out before we launch into some coding is I've recently installed a second camera. So this is a camera which is pointing down at my desk, and I just want to switch over to that just to give it a quick test. And hopefully in the field of view of the camera will be a quick clue to what we're going to be doing on probably every other stream, starting Wednesday, I'm hoping. And we're going to be doing something a bit different from programming, so the clue will be in the picture. So let's quickly just switch over to the desk cam and see what that looks like. So there we are, this is my desk cam. Hopefully we can all see that okay. And the clue is we're going to build a Saturn V on stream. Starting, I'm hoping, Wednesday by building stage 1. It's using a well-known block-based construction system, and it's a pretty beefy kind of model. It's about 1 meter tall, and I'm hoping it's going to look really good at the end of it. So that's a good enough test for the desk cam. It looks okay to me, so I'm hoping that will be okay on stream. Okay, back to the coding. Back to the coding scene. So, okay, so what we're going to do today? Well, over the weekend, I started doing some work on the rotate and shift operation codes, and I've done a fair few of kind of right rotate and left rotate commands, which kind of shift bits around inside a byte. usually the accumulator, sometimes in a register or in a memory location. And so I thought we'd do a bit more work on that. And what I'd like to look at, let's put that booklet away. What I'd like to look at is some shifts. We've done rotates, so I worked on that, and I can show you that later. But let's actually get some coding done, because that's what we're here with, a coding stream. So let's go and have a look at the user manual. So this is the official Zilog Z80 CPU user manual, and it has a description of all of the operations which are documented for the Z80. Now, I say documented because there are undocumented commands as well. So I think what we'll start off with is this SLA command, which is shift left arithmetic. That's what it stands for. And you can see it's going to operate on some piece of data, which is represented here by the letter M. And M is going to either be a register. So this is the block of byte codes which are going to represent SLA against a register, against a memory location pointed to by the register pair HL, or these indexed versions of it. And we're going to kind of basically concentrate on the top two for now. So what is a shift left? I'm going to move this off screen so I can refer to it while we're coding. So what is a shift left arithmetic? So we better explain that, I think. So let's see if we can describe what that is. Let's bring up whiteboard. So if we have a value, so for example 1 0 0 1 0 0 1 0, we want to shift that to the left, and the way it shifts in this particular operation is it actually shifts via the carry flag. So we have a register which is a set of flags, one of which is a carry flag. I'm going to start carry, and I'll learn to use this pen and graphics tablet eventually. So we want to do a shift left arithmetic. So S L A, and the important thing is the arithmetic part, the A there. It's going to dictate what happens when we move this whole set of binary digits to the left. Remember, we're going to move them this way. So what happens is this 1 will go into here, into the carry. And what happens at the end, everything else moves up 1. Oops. Oops. Sorry. Yeah, that goes to there, that goes up to there, that moves up to there, etc. We're going to skip along. And what happens at the end, in an arithmetic shift left, we're going to push in a 0 into the end. So in this case, what we'll end up with will be a 1 in the carry flag. The carry flag will be set, and then we'll have 0 0 1 0 0 1 0 0, and that'll be the result that we're after. Carry flag will be set. So this is one of the kind of basic operations. We'll also look at the shift right, the logical shift, and there's a whole bunch of things. But this is a shift. This is rather than a rotate. With a rotate, what happens is we have whatever's in the carry flag would go round and come in on the end instead of this 0. With a shift left arithmetic, we're pushing this 0 in. That's kind of what we're trying to actually achieve. So we better write some code. So let's just grab this block of comment here and just comment out our first instruction. So this is shift left arithmetic, and we're going to operate on a register, and we're going to call that register R. So we're going to say that in the description R is shifted left, 1 position through the carry flag, and then we're going to say that 0 is shifted into bit 0. A0. So that's a description of what happens. Then we need to figure out what flags are affected now. So let's go over to our description again. It will tell us here what flags are updated, and most of the tests that we kind of have to satisfy when we're kind of working out whether our emulation is any good or not is whether our flags get set correctly. So it says that flag S, which is the sign bit, that's going to be set. Z will be set. H will be reset, which means set to 0. The parity overflow flag will be set if the parity is even. C is reset, and the carry flag is the bit that comes from bit 7, as I described. So in fact, all of our flags are going to be updated here. Let me move that off screen again. So this is correct. We're going to say all flags are going to be updated, and we need to kind of set those flags. So let's set ourselves up with a command which does nothing. So we're currently I'm returning a byte from all my opcodes. Currently, and it's always 0. There was a kind of an idea that it was going to, if there was an error condition, it would return a 1. It's not necessarily ever going to happen, but I may build that in. So I'm going to leave it in there for the moment until it's proved that I ain't going to need it. One way around, we should add it when I do need it, but I started off with that design, so I'm going to keep with it. So this is shift left arithmetic, and the R in the command here, the command name, function name, is simply a register, and then we're going to return 0. So there's a command which does nothing at all, which is exactly how we want to set it up. Now we need to actually go through and put those commands into our command tables. This is our opcode table, so it's quite extensive. As you can see, we've got quite a few opcodes already set up. These top ones here are root instructions. These are operations which the actual opcode is a single byte. There may be a multi-byte instruction in terms of data that it uses, but actually the actual command is a single byte. And then we've got some more tables down here. We've got ones which are double byte commands or opcodes which start with DD, ones that start with FD, ones that start with ED, and ones that start with CB. In fact, we've got some also triple byte instructions start with DD, CB, and FD, CB. So these particular commands that we're dealing with, the shift left arithmetic of a register, we need to have a look at that, see what those are. So these are going to be commands which they're double byte commands which start with a CB. So we're going to be working in the CB instructions table, and if we scroll down here, this is a list of all of the opcodes. So the ones in capitals are recognised ones. The ones in lowercase, I believe, are perhaps not particularly documented instructions, but ones which do work. So we've got this block here, shift left arithmetic, and then we've got the registers. So if you've watched the streams before, you'll know that we have a number of registers available to us. We have an accumulator, which is A, which is this one here, and then we have register B, C, D, E, H, and L, and those are 8-byte registers, and that's very, very fast memory inside the CPU itself. And this brackets HL. HL is what's called a register pair. We can join these two together and read them as a 16-bit register, and the brackets means the location pointed to by. So this is actually shifting left arithmetic, the data at location pointed to by HL. So we're going to do that block of instructions. We're not going to do the HL one straight away because that's a slightly different command. We're going to work on A, B, C, D, E, H, and L. So that is basically 2.0 all the way through to 2.7, as you can see there. So CB 2.0, CB 2.1, etc., all the way to CB 2.7, and we're going to skip out CB 26 or 2.6 initially. Okay. So let's get those instructions in place. So what I'm going to do, in fact, I'm just going to copy this whole block here and put it down here. We're going to get rid of that one there. That will correspond to 2.6, CB26, and I'll explain what the instructions actually refer to. Let's first update these values to reflect what our operation codes actually are, and we'll quickly change these mnemonics. So this is the mnemonics are going to be there so that we can disassemble our machine code at some point. We're going to need to write a debugger, a disassembler. There's quite a lot of stuff to do. I think my debugger is going to be a WPF application, which should be quite fun to write. So this is shift left arithmetic of B, and then what we can do is we can. My Alt key is not working very well on this keyboard, so I'm going to have to write them in. I was going to do a block update there, but not going to play for me. Let's update all those. Luckily, because there are patterns in the way the opcodes are created within the CPU, that these kind of patterns do repeat. So as you can see here, we've got a rotate left and a rotate left through the carry flag. So there's kind of nice patterns going on. Okay, so what's next? We've got a mnemonic for what the instruction disassembles to, and we've got then a couple of functions here, which are the addressing modes. Now, IMP stands for Implicit or Implied addressing mode. What that means is that where the data comes from is implied or implicit with the operation itself. In this case, you can see that SLA B is going to operate on the B register. SLA A is going to operate on the accumulator. So we don't have to get the data from anywhere else. It's implied by the actual command. That's why we've got an imp here. The reason why we have two addressing modes is that some commands actually do have they get two pieces of data. So they might get, for example, they might get an offset, so a signed byte from -128 to +127, and then they might get a memory address in 2 bytes. That's why we have two addressing modes. And then we have the command that's actually going to be run. And this is another, once again, a function, and this is where we put in our SLAR. This is the command we just defined, which doesn't do anything at the moment. I must sort out my keyboard because it's much nicer to do this with a block edit. And I've actually just noticed an error. That there should be that. So that's good. Noticing the errors is a good thing. So that's a copy-paste error. So yeah, I do copy-paste far too much on stream, really, for my own good. So it's good I spotted that. Okay, so the next thing is what we call the timing. So this is how many. So the number of digits is how many machine cycles the command takes, and the individual number is how many clock cycles each machine cycle actually consumes. So if I go here and bring over the that's the wrong one. This one here. Bring over this in the user manual. You'll see that it'll describe how many machine cycles, M cycles, and then T states the instruction actually consumes. So this is 8 for 4 and 4, two machine cycles in total. And what we're trying to do is emulate the timing of the CPU as well as the function of it. So, machine code obviously consumes clock cycles. The more complex the command, the more that the CPU has to do, the longer that command takes to actually execute. And what we want to be able to do is emulate that feature as well, so that there is a cost to to using the more complex commands, the multi-byte commands, the automated commands. And that way we learn about optimizing our code when we write in assembly language, the ultimate optimizing experience working with assembly language. So we could see there from that SLA R takes 2 cycles, 4 and 4, and that's exactly what we've got here. So 2 cycles, 40 states each. And what happens on the first machine cycle will be actually getting the command out of memory, pointed to by a special register called the program counter, and actually decoding and executing it, and then the second machine cycle here will be actually doing the operation on the register. And you can see that actually the number of clock pulses each machine cycle takes can vary. So the first one usually is a 4 because that is fetch the opcode and decode it, but you can see sometimes that things take a bit longer, 5 clock pulses, or a bit less, 3 clock pulses. And here's one here that took 6 clock pulses to actually do. So we have to kind of pay careful attention to those if we want to get our emulation correct. Okay, so now we have our CV 202. Oops, that's really wrong, isn't it? Where's C? There. CB 20, 21, 22, 23, 24, 25 and 27. So we should be able to build without any problems. So now we've set ourselves up to write a test. So let's go over to our tests. We're working with 8-bit rotate and shift commands. So we've got a special class where we're going to put all those bits. Okay. So we haven't got to go overboard in writing the test. We can work with a couple of instances. We haven't got to write. If we're going to assume that if we get one register working, all the other registers will work, especially as we're going to be reusing code to select the data out of the registers, and that's been well tested by previous tests. So we shouldn't have to do an awful lot. Let's start off with a private void method. I don't know what, I'm going to just call it test for now, and let's decorate that with the fact attributes. So that fact is part of XUnit. Okay, Brandonius, welcome to the stream. Good to see you. I've got a command for you there. The dev chatter command. Let's see if it works. There we go. I can confirm that all my games are rigged. Dev chatter. There we go. Okay, so welcome to the stream. Good to see you. Where are we? Okay, so we got our basic test set up there. So what we're going to do. So I'm using Fake It Easy, and Fake It Easy is a really good way of kind of encapsulating fake commands and doing so in very small, simple kind of language. So what I'm going to do is we're going to grab a fake bus. So our fake CPU is going to be connected to a fake bus, and the fake bus basically is just connected to some RAM. The RAM, of course, is just a dictionary in this case, and it's a dictionary, so we can have non-contiguous elements in our random access memory, or our fake random access memory. In the actual emulation, of course, it'll be an array, but we can do this easier to have this kind of non-contiguous memory using the dictionary. So I'm going to grab this bit of code here, which is setting up our memory location, and the Fake It Easy part. So we've got a fake IBus. IBus is an interface. There is no concrete implementation of IBus. It simply it defines there are two in fact there are 4 methods, but the 2 methods we're interested in are read and write, and that's going to read from memory and write to memory. In this particular command, all our data is going to be pre-set up in registers in the CPU, in the fake CPU, so we don't need to actually write any data out to memory. So we've got we've got every time we get a call to read, it's going to have a memory address and a boolean. Then we're going to return lazily the data that's at the address. So program with a key of ADDR. What that means, every time it calls, it's gonna go and figure out what's the next piece of data I need to get. The next piece of data it's going to get is going to be controlled by our program counter, and we've got code within our emulation which advances the program counter. It increments it one step at a time as we go through all of the operations to get the actual operation itself, the opcode itself, and then any data associated with it. So our program counter should always be pointed at the next command we're going to process. Okay. So what we're going to do, we're going to do a shift left arithmetic, and we're going to operate on I don't know, the B register, and that was CB20, wasn't it? CB20. In this case, we don't need any data within our data block. We can set that 0, and now we need to set our CPU up. Up here we can go and look at that. I will grab these next 2 lines and bring them down. Okay, so what we're doing here, so we get creating a new instance of the Z80 emulation, and we're setting up our internal registers. The program counter is going to point at the next command we want to execute. So that's 0080, which is called this command here. Now we need to set up our registers. In this case, we're going to operate on the B register. So we can set B equal to something. And what I like to do is go and have a look at the user manual, because it'll have an example operation. Let's go and have a look at that. Come on. Let's get this over. There we go. Okay, so it's saying that an example would be 10110001 in A register. It's saying the L register. It doesn't really matter what register it is. Should we use the L register? Yeah, let's use the L register as well. So L. So if we go back over to here, L, shift left L was 25. We use 25 as well. And we'll say the L register is going to contain, and we'll put it in as a binary number. I'll just bring that across here again. So that was in binary as 10110001. So that's setting up our register, and we're going to do a shift left arithmetic on that. So if we go over to our whiteboard again, I'll just do some erasing. So what we're saying is we're going to have 1. Keep pressing a button on the top of my pen. 1 0 1 1 0 0 0 1. I think we said. Is that what we said? Oh look. Yep. And we're going to do a SLA on that, a shift left arithmetic. So what's going to happen is that in our carry bit, that 1's going to go into there, then we're going to have 0, 1 1 0 0 0 1, and then we're going to push in. Remember that 1 is going to go into there, and we're going to push the 0 in, and then everything else is going to move along this way. So the result should be, the carry bit should be set we're going to have 0, 1, 1, 0, 0, 0, 1, 0. So we should be able to set that up as a test. Probably get rid of that. Okay. So the next thing we need to do is actually step the CPU through through one command. So we've got a command that we wrote a couple of streams back now, which was step. That'll step through one command. So basically it's going to execute db25 for us. And then we should have the result, which will be still in the L register. So we can assert is true, or R equal. So we're going to say that 0b 0, 1, 1, 0, 0, 0, 1, 0, and the contents of L are going to be identical. So is equal. Is equal. Equals. Equal. You forget. I use different test frameworks at work than I do on stream. So what it is. And the next thing we're going to assert, because we know the carry flag should be set, because we shifted a 1. We shifted this 1 in bit 7, shifted it into the carry flag. So let's assert true. And we're going to say that CPU.f, which is the carry flag, and we're going to AND that with Z80.flags.c. It's going to equal Z80.flags.c. So that's basically saying the carry flag is set. So that's the basic test that we're going to start off with. There's more that we need to do. Okay, so this is, we're going to say updates register correctly when shift left arithmetic R. And I need to think of some better names for these methods, but that seems to encapsulate what I want to do. Okay, so let's run our tests. So we should expect it to fail because we're not actually doing anything in terms of the code. So we got a nice failure. So that's our red stage of red-green refactor. So what it's saying is that it expected, interesting, it says it expected 98. It actually got 217. So it's interesting how it expected anything, to be honest, isn't it? I think basically this is that's 177 is this value here, the unchanged value. So let's just bring up our programmer's calculator, and there we can stick in go to binary 1 0 1 1 0 0 0 1, and that once again is 177. So that's basically the unchanged, the unshifted value, which is why it's saying it's expected 98 but actually got 177. Okay, so the next part, we need to get the value of whatever is in our register. But we want to do it in the generic way. We've already got some code written which helps us with this. And if I go and get the instruction definition here, you can see that for this particular command, SLRA, then these 3 bits, 0, bit 1 and bit 2, are used to define which register we're going to be reading and operating on. This is the implied or implicit part of the addressing mode we're using. It's actually built into the operation code. So the definition here is that if it's all zeros, those 3 bits are zeros, it's register B, etc. So it's got 0, 1, 2, 3, 4, 5 and 7. 6 is missing. 1, 2, 3, 5, 7. Okay, so we need to actually get hold of those the least significant 3 bits of our opcode here. So we can do that. We can say var source register is going to equal, so we need our operation code, and we're going to AND that with a mask like that. Okay, so that's going to give us in there whatever the last 3 bits of that operation code were, which are going to indicate which source register we're going to use. Then we can use some code we've already written. We can say our value n is going to be, I think I called it read from register, and in there we pass the source. Okay, so what does read from register do? Let's just pop over and go to it. So this is one of my favourite features of C#8. This is the switch expression. So we're passing the source in, and then we're going to return. If src was 0, we were going to turn the contents of B, 1 the contents of C, etc. And you can see that we have the last element here is a discard. With a switch expression, it has to have every single possible value. Yeah, gotta love those switch expressions. And the programmer's calculator. It's very, very useful, especially I guess with Interactive 7 Brendonius when you were working on that, and also obviously in this to look at results. It's very, very useful. The discard, because we have to have every single option, we can't have any missing values. Basically, if it's neither 0, 1, 2, 3, 4, 5 or 7, we're going to return just 0. Not perfect, but it's good enough for what we're doing, because the opcodes actually can't give any other values than those. Okay, so now we've got our value n into the register. Now we need to actually do the operation. So what is the operation? So we're going to shift everything to the left, but we need to know what bit 7 of our value n is. So we're going to create a variable, call it new carry. That's going to be whatever bit 7 was of n. That's going to be n, and we're going to AND that with that bit pattern. So we're looking at what is the value of bit 7, and that's going to end up in our new carry. Okay, so then we're going to do a shift left, so that n is going to equal n shift left by 1. And we're going to have to make that into a byte. Okay, so that's our value of n. We know that we want to set the value of new carry, of the carry flag rather, to whatever is in new carry. It's either a 0 or a 1, isn't it? So what we can say is we can say set flags, and our flags.c for the carry flag, and that's new carry greater than 0. That should satisfy our test. Okay, so what we're doing here, we're saying we're going to shift our value to the left by 1. We're going to set the carry flag, but now we actually need to write this value n back where it came from. So we have another equivalent of read from register. We have, I think I called it a write. I called it write to set, was it? I don't know what I called it. Read from register. Register. Let's have a look. Let's roll up and see what I called it. I thought I called it write to register, mustn't it? Assign to register. There we go. A. The naming is hard. Assign to register. We're going to pass in where we want which register we want. It's going to be the same as the source, and then the value is n. Okay. So now we should be able to run our test and see what happens. And it passed. Okay, which is great. However, we aren't finished, because if you remember when we said up here what flags are affected, actually all the flags are affected. So we've got to work out what to do with the rest of the flags, including the undocumented flags. So let's go and have a look back at the documentation, and it will tell us what the flags, what happens to the flag. So it says that the S flag, the sign flag, is set if the result is negative, otherwise it's reset. Let's tackle that. Okay, so we're going to set flag flags.s. So what does it mean if the result is negative? We've got a binary number here. Well, a binary number with a 1 in bit 7 could be a negative number if we're dealing with signed bytes. When we do this kind of operation, if the sign bit 7 is set, we say that could potentially be a negative number, so we set the sign flag. So basically what we can say here, we're going to set that if n is greater than or equal to the hex value 80. So that means that bit 7 is a 1, and so we set the sign flag. It's a potential negative number. Not saying it is a negative number, depends on what we're doing in the context of our program, but it could be a negative number. The next flag it says is that the Z flag, the 0 flag, is set if the result is 0. So that's fairly simple. Set flag flag dot Z if n is 0. Okay. Let's just fix up that. That's an S, not a one. It's a capital F. Okay. The next one. It's going to reset the half carry flag. Flag H is going to be reset, which means it's set to 0 or false. So I'm going to set flag flags H false. The next one it wants to look at is the parity stroke overflow flag, which is flag P stroke V in the documentation. I've just called it flag P. So set flag flags .p, and that's the parity, set to the parity of n. So what is parity? You might say, well, we have two types of parity, odd and even. If the parity is even, it means there are an even number of ones in the byte, and if there's an odd number of ones in the byte, then it's odd parity. And parity will return true here if it's even parity. So for even parity, we set the parity flag to 1. We have a flag called n. The n flag is a flag that is not really used by programmers. It's used internally. And basically what happens with the n flag is that if we're doing a addition, what's it doing? Changing that itself, isn't it? If it's doing an addition, then we want this set to false, and if it's doing a subtraction, it's set to true. Here we're doing neither. This is going to be set to false. And the reason the N flag exists, and the reason why we're interested in whether we're doing subtraction or addition, is for binary coded decimal. And we'll get into binary coded decimal at a later date. But that's a way of encoding decimal numbers in your binary into binary bits. It's not the same as hexadecimal, it's completely different to that, but it's actually a way of getting the numbers 0 to 9. In fact, you use 1 byte to represent 2 digits in binary coded decimal, and there's some kind of trickery you have to do to make that actually work. Okay, and the last is the carry flag, and we've already set the carry flag. Now, there are some undocumented flags. Documented flags. There's 2 undocumented flags. I'm just going to copy the values. They're always the same. Well, mostly the same anyway. Flags X and flag U. And basically they are copies of bit 3 and bit 5 of the result. Now, it's not always quite as simple as that. There are some wrinkles about undocumented flags. They are undocumented, for example, is one of the wrinkles. And a fair amount of investigation has been done into how these flags get set. On the most superficial level, this is true. They're set to bit 3 and bit 5 of the result. And that's kind of most of the time, but there are cases when that's not the case. To cover for one of those cases where it's not the case, we have to save the results, save those flags we've just set in a temporary register called Q. Whether this register actually exists in the actual CPU is a matter of conjecture, but we've got one. We've got a Q register, and basically all it does is store the values of the flags. And what happens is, in certain commands we will look at the flags that were set by the preceding command, so we can figure out how to set the undocumented flags in the current command. We haven't reached any commands or any opcodes that require that yet, but because we're going for the most accurate emulation we can, we need to cope with these really weird behaviour of these 2 undocumented flags. So we do this set Q. There's two methods on the CPU for this: set Q and reset Q. Some commands will actually reset. If it doesn't change the flags, we reset, set them all to 0 in the Q register. It's basically a temporary copy of our flag register. Okay, so we've got that now. We should be able to. We haven't tested any of these flags, so we should be able to run our command through the test, and it should still pass because we're not testing the values we've set here. Okay, so let's go and have a look at now changing our test. So we need to do some assertions. So I'm going to assert false on all of the flags. So what I'll do is quickly just copy these into here. So we're going to have the sign flag. And then there was the 0 flag, Z. Okay. And then there was the half carry flag, which is flag H. This half carry flag is usually set when there's been a carry from bit 3 in a nibble into the next nibble, bit 4. So it's all to do with this binary encoded decimal stuff again. Then we've got the parity flag, parity stroke overflow flag P. Then we've got flag N, which was the addition subtraction flag. And we've got what we get then. We've got like a X and U, the undocumented flags. So we've got those all set up. So let's go and figure out what should happen. So let's bring up our whiteboard again. Where's the whiteboard? Okay, so we know the carry flag is set. So that's good. So we've already tested that works. So what's the parity of this? It's got 3 ones, so it's odd parity. So we think that the parity flag should be 0, unset. Is it 0? No, so the Z flag should be unset. Isn't it? Oh, what else have we got? We've got the sign flag. So the sign flag, we're going to look at bit 7, and it's whatever value's in there, so that's a 0 again. That's not set. The half carry flag we know should be 0 because it's set to 0. And we've got the carry flag and the end flag. So these 3 values are correct. So if we run our test now, so it's false, false and false. We run our test, we should still pass. And we don't. Okay, so what happened? Let's have a look. It's saying it expects the flag U to be true. Let's have a look. This is one of our undocumented ones. So bit 3, 0, 1, 2, 3 is 0. That's X. And here's bit 5, and that's set to 1. So bit U will be 1. Okay, so our test has caught that. We didn't take account of the undocumented. Yes, undocumented flags rather. So let's set that to true. And now we run our test again. And we pass. So what I'd like to do is have another test. Let's call this S2. Okay, so what value should we put in there then? Well, before we had a 1 in bit 7, and that gets shifted into the carry flag. Let's this time put a 0 on the front, so we have 0, 1, 0, 1, 1, 0, 0, 1. So we expect our result now to be 1, 0, 1, 1, 0, 0, 1, oops, 1, 0, 1, 1, 0, 0, 1, 0, don't we? So now this 0 here would have been rotated into the, or shifted into the carry flag, so the carry flag should not be set. It should be false. It's not set. What else have we got? So let's have a look. How many ones are there? There are 4 ones, so we've got even parity. So we think our parity flag should be true here. Okay, so let's have a look. It's not 0. The half carry flag is definitely going to be unset because we do that. We set it to false anyway. The sign flag. Well, we've just shifted a 1 into bit 7, so I think the sign flag should be true. Okay. So now in the results we got 1, 0, 1, 2, 3. So flag X should be unset, but there's a 1 in 5, so flag U should be set. I think that should be correct. The end flag is always false because we've actually explicitly set it to false. So let's run that test. And we're green. So now we've kind of pretty much exercised all the different flags. I guess the only one that didn't really change was the parity flag, but that's okay. We've tested the others, and I think that should be fine. And we'll do obviously more in-depth testing of those values when we do the validation testing. What I'm going to do though, I'm going to change which register that we're working with. Let's go and have a look at a different register. So let's use, I don't know, let's use E. So E is 23. So let's go over here. Let's change this to from 25 to E, to 3 rather. That'll be working on register E. Register E needs to be what we set up, and register E needs to be what we test at the end. So just so we've gone 2 different randomly selected registers, and that should still pass, and it does. Okay, so we've got a nice bunch of commands added. So we've got now a gap here though, so we know that there is a command which is 26, CB26, which operates on the memory location pointed to by the register pair HL. So let's add that in. I'll just copy this line down. This is going to be 26, and it's going to, the way we indicate that it's a memory address pointed to by a register pair is like that. So brackets indicate pointed to by, and we've got HL, which is a 16-bit register pair. So it's H and L. H standing for high byte, L standing for low byte, obviously. But we can actually do the same kind of thing with BC and DE. So this is no longer going to be implied addressing. This is going to be an addressing mode called register indexed HL. It's no longer going to be SLAR, we're going to call it SLAH, and our timing is going to be different. So let's go and have a look at the timings on that. So here we are. So here's SLAHL. It's 4 machine cycles, 4, 4, 4 and 3. So we need to put that in 4, 4, 4 and 3. So it takes an awful lot longer to actually do that. That should be alright. Why is that white? Okay. So the reason why this is underlined is we haven't actually got a command that fulfills that yet, that function. Let's go and write that. So we'll get some documentation. So this is going to be SLAHL, and we're just going to document it like this. So the register, the data located at the position pointed to by HL in memory is shifted left 1 position through the carry flag, and a 0 is shifted into bit 0. It affects all the flags again. In fact, it's going to affect all the flags exactly the same way as above. So what I think I'm going to do is I'm going to extract this out into a method. So everything except new carry is going to depend on the final value. The carry flag is set completely differently. So let's extract this block of data, this block of commands out into a method, and we'll call it set shift left flags. And I'm going to copy that, and I'm going to put it down into my helper methods at the bottom here. This means that we're not going to have to write that logic again, which would be good because you don't want any kind of errors creeping in because of incorrectly setting those flags on many commands. So let's set up our command again. So private byte SLAHL we called it, and that's going to take a byte, which is an opcode, and it's going to return 0. Okay. So we need to test. Okay, so what's our test going to be? Well, we could, in theory, we could just take this test and repurpose it, and we'll do that. Okay. So updates location pointed to IHL. And then the command we're going to run is SLA HL. Okay, so we want to run that command, don't we? And that was 2.6. We know that. So we need a memory location that we're going to put some data in, and I think what we'll do is use this memory location here, and we'll use the same piece of data we tested here. We're going to put that piece of data into that memory location, and we're going to then set H and L. Now H and L are 8-bit registers, and we can pull data out of them as a 16-bit value, but we can't write into them currently as a 16-bit value. Ancient Coder, welcome to the stream. Good to see you. Fuel Stable, welcome. It's a little easier to understand CSS. I can't understand CSS. I find that impenetrable. Okay, so the top byte is going to be 01 for our memory location. OX01, and the low byte is going to be OX, and it was 91. That's the memory location. This HL is going to point to the memory location. So what we can do is indicate that like this. So that's what we're pointing to. So that's what's going to change. And instead here of looking at CPU E, Cornel, thank you for the follow. That's wonderful. Let's give you some Electric Alf hype. This is one of Fuel Snable's fantastic shaders. If you haven't caught our joint shader streams, then we've done currently about 6 of them, going from kind of 2D shaders all the way to fantastic 3D terrain shader, where we fly over mountains and valleys and lakes and forests with mist and clouds in the sky and everything. So do follow those. So that's one of these pixel shaders that we've been working on with Fuel Snable, and we've got a nice hype there. So thank you very much for that follow. Actually, what are we now? We're at that's 235, 325, is it? 326. That's we're heading towards our target. That's really great. Okay, so the location we want to check as the new value is program, and it's going to be the contents of HL, and that's what I say we can actually reference. CPU.hl, CPU.hl. We can read the register pair as a 16-bit address. We just have to write it in individual bytes like this, high and low. In fact, if we're reading from memory, we actually read it in the order low byte then high byte, because the Z80 is a little endian processor. So, but in this case, we can write it quite succinctly with H and L, because actually stand for high and low. Quite good. Okay, so we know the flag should be correct in this case. So we're going to run this command, run this test, and it's going to fail. Of course it is, because we haven't done anything. We haven't decorated it with a fact. Let's run it now. It should appear there. That's it. It's appeared now. Run it and it will come red. Okay, and it's going to be failed for the very basic reason that 89 is not the same as 179. So there's a piece of code missing here, because we need to actually write this value out to memory. So we need to go and get the second part of our fake it easy code, which is the fake for the writing of data to memory. So let's drop that in here. What this is going to do, it's going to say, okay, when you receive a an invocation of write to an address with a byte, it's going to invoke a local function called update memory, and it's basically going to update this dictionary here, and it's going to say that at key ADDR it's going to stick the data. So we need also to grab the local method, local function, update memory. Pop that in the bottom there. And see, all that's doing is actually setting program key to the data. Okay, so if we run that again, it'll still fail because we're not actually doing anything. It's exactly the same. Okay, so we need to go and write the code then. Over here. So what do we need to do? So we need to get the value that is at location pointed to by HL, and we can do that quite easily. We have the technology to do that because we've already written methods which help us do that. So we have a fetch. It's actually called fetch1 because it's the very first fetch. So that using memory addressing mode 1, which is the first addressing mode, and we're going to fetch 2 equivalent, which uses the second addressing mode. So it's this addressing mode we're going to use. We're going to use the register index HL. So basically what that means, all we're going to go is we're going to go and grab whatever is at the memory location pointed to by the HL register. And in here we need to pass in which operation instruction table we're using. And we're using the instruction table underscore CB instructions. Okay. We need to do that because the same operation code, for example 2.6, could be defined in several other instruction tables and may have different addressing mode. So we need to get the addressing mode from the right instruction table. Okay, so we've got our piece of data. So now we need to do something similar. So we need to do var new carry and equal to the value of n, and that with it'll be 3, 2, 3, 4. Okay, so we've got the value of our carry, and then we can set our carry flag accordingly. But what we're going to do then is we're going to do the shift. The m once again is going to be as to a byte of n left shifted by 1. And then we're going to write that data out. We're going to write it to the location pointed to by HL. And so we're going to use write to bus, and then the value HL, and then n. That's our data being written back out to the memory location pointed by HL. Then we can set our carry flag. So this is going to be flags C and new carry greater than 0. And then we can use exactly the same method that we just extracted, set shift left flags. But what we'll do, we won't do that, and we'll just see how far we get with the test, just to show that we should get past. So the very first test is that the value is equal, and then that the carry flag is set or not set. In this case it should not be set, so we should fail, for example here on that assert there. So let's run it and see where we do fail. So yeah, so expected false, it actually was true, and it's on the carry flag. Is that right? Shouldn't be set. Let me have a look at that. The carry flag shouldn't be set, so if I made a mistake, let's go to instructions. 1, 2, 3, 4, 5, 6, I missed a zero off. There we go. We'll run that again. This is what a test is for. We've caught a typo. So now we've got expected true actually is false, and this time is the sign flag, which should be set because we've shifted a bit, a 1 into position 7 there, bit 7. So we can go back and we can fill in the last remaining command, which is to set the shift left flags. And we pass the value n into that. And run again. And we passed. Okay. I'm just going to write down what we've done. SLA R and SLA L. I don't intend to go through all of these variants. There's some more variants of SLA that we could do, but I'll do them off stream because we've kind of pretty much demonstrated what a shift left arithmetic is. So let's go and have a look at our documentation and see what else we can do. So there's shift right arithmetic, and I think that's one of. No, I don't think we need that. So that's exactly the same concept, except we're shifting to the right. I want to do a shift right logical, and the reason why I'm choosing particular opcodes is because I've got an assembly language program in mind, which would require a shift right logical, and this is the shift right logical. We're going to do that one. Okay, so this is very similar. So what happens is we're going to push a 0 in. Let me bring this across. We're going to push the 0 into bit 7. Everything's going to kind of shuffle along by 1 to the right, and whatever's in bit 0 is going to end up in the carry flag. So we should be able to write something like that, fairly simply. Grab. I'll leave some space because we've got some missing code. So this is shift right logical. Of a register R. That's up R, so R is going to be shifted right one position to the carry flag. A 0 is shifted into bit 7 this time. Okay, and all the flags are going to be affected as before. Okay, so we need outcodes. So this is shift right logical. So you can see there's a shift right arithmetic block here, and then the shift left, shift right logical. Here we are. So this is the block of opcodes we're interested in. So this is CB again, so this middle column is CB. It's a double byte command, and 3839, etc. So let's make that 38. Okay, so we need to set those up in our operation table. So that's the CB table, that's over here. So what we can do is you can over here, let's do some dangerous cut and paste. So you need to keep an eye on me here, make sure I'm not making any mistakes. We said that was 38. Maybe 38, 39, A, B, C, D, F, and we're going to remove that one for now. That's the one that's going to operate on the register pair, and I deleted too many rows. Just this one here. Okay. So if you need to kind of get my attention, there's a exclamation point hey command. I'm not able to see chat at the moment very easily because I've only got two monitors, one of which is very small. So if you do need to can ask me a question about this, just use the exclamation point "Hey" command, and should hear an alert that you want to talk to me. Okay. So these are shift right logicals. My Alt key was working properly. I don't know what's wrong with my Alt key. It doesn't seem to want to. Not logical, so I have to change them by hand rather than use our nice block select. It's doing something, that Alt key, isn't it? Because it moved that again, didn't it? I'm not sure what it's doing. Weird thing since I had a Windows update a little while back. That's when my audio went a bit crazy, and a few other things have gone crazy as well. So, shift right logical of the accumulator. It's all implicit or implied addressing. It's all 4 and 4 in the timings, but the command this time is going to be SRLR. All those. RL. There we go. Okay, so we're set up so we can write some tests. Yep, we've got a basic thing there. Open references, which is good. Okay, let's write a test. So what we can do is we can first register correctly. Let's grab that one. Now you got to be careful when you're copy and pasting tests like this, but you'll keep me honest, I'm sure. So this is shift right logical. That, and we can do a different register. We can register D, and register D. If we go to our Z80 instruction set, register D would be 3A. This is going to be 3A. Shift right logical, register D. Okay. So let's pop that value there into D, and let's work out what actually that means for our value. So our value, I'll just make a note of it, is 1 0 1 1 0 0 1. Okay, so it was our starting value is going to be 1 0 1 1 0 0 0 1, and we're going to do a shift right logical. Basically means we're going to push a 0 in from this end, and whatever's in here is going to drop into the carry flag, and then we're going to shift 1 right, so it's going to start 0 1 0 1 1 0 0 0, and a 1's going to end up in the carry flag. Okay, so that's our first kind of test that we can write. So it's going to end up as 0 1 0 1 1 0 0 0. No, let's do that. Now our value in D is going to end up to be 0 1 0 1 1, pardon me, 0 0 0. And a 1 is going to end up in our carry flag. So we'll comment those parts, those assertions out, and we'll see if that's actually what's going to happen. Obviously it won't happen. Right, so we fail on quality and all that, so it's fine. So let's write some code. So, as before, the source register is going to be equal to the opcode. We're going to AND that with a bit mask for the last three bits. So that gives us an integer between 0 and 7, and then we're going to say 10, our value is going to be read from registers that was our switch expression, which basically brought us back the right data. Okay, so we've got our value. We want to know what the new carry is going to be. That's going to be whatever is in bit 0. So what we can say is we're going to look at n, and we're going to AND that with a bit mask. That 1, 2, 3, 4, 5, 6. That's going to be our new carry, and we can then say that n is going to be a byte, and it's going to be n shifted right by 1. And then we can, it was assigned to register wherever it came from. We put it back, we put n back into that, and then we can do our flags, and we can say that set flag flags C is going to be new carry going to 0. Okay, so that should actually satisfy the test we've got so far. Let's give it a go. There it does. So now we'll bring in the rest of the assertion. So let's go back and have a look at the data that we've got here. So in the result here, the sign bit is not going to be set. So that's a 0. The parity is 0 because we've got 1, 2, 3 ones. That's odd parity. It's not 0, so the 0 is not going to be set. So what else happens on this? Let's go and get the user manual again. So it actually says it actually operates completely differently. Look. So in this case, the sign flag is reset, so we don't care. The Z flag is set if it's 0, H is cleared, TV is parity, so N is reset, and C is the data from source register 0. So interestingly, the only things that get set actually, according to the based upon the result, are Z, P, and C. We've already done C, so let's do Z and P in our code. And this is where you've got to kind of be a bit careful not assume stuff, because you could almost think it's going to be the same, but it isn't. It's actually completely different. So we're going to say set flag flags.z. That's going to be if n is set to true if n is 0, and set flag parity flag. And that again, and then we'll pass the value of n into the parity function. So those are the only values that actually get set. Those 3 values actually only get set based upon the result. but we haven't done the undocumented flags yet. And then the rest of them just get set to false. So flag flags.z false. Set flags.h false, and set flags.n false. And I'm going to use a codeless feature here. You notice my cursor is before closing bracket. If I press semicolon, it just knows by magic and puts the semicolon after the closing bracket, which is really good, especially for people like me who struggle to type on screen. Okay, so let's have a look at the undocumented flags. In here, in our result, 0, 1, 2, 3, that's a 1, so x should be a 1, and this is u is a 0, so flag x should be set. Go and have a look at our test. We can just, in fact, because the undocumented flags in this case are basically the same. We'll just go and grab the code from. And we need the set Q as well. So let's go and look at our test again. So we said that the sign flag would always be false. The Z flag, it's not 0. The H flag is always false. It's an odd parity, so P is false. X we said was true. Bit 3. And then bit 5 was 0, so that's going to be false. Let's run that. And it still failed. Okay, so that's interesting. So what's it failed on? It's failed on flag X. So maybe I've got my flags mixed up. Let's go and look what X is. X is bit 3. Go back to our whiteboard. So 0, 1, 2. Bit 3 is a 1 according to this. Oh, yes, bit 3 is a 1. Why does it think not? Okay. So here, 0, 1. Definitely a 1. Ah. Aha. There we've got an error there. So is that been repeated elsewhere? It has. Oh yeah, this is once again copy pasta. So once again our tests help us figure out we actually coded something completely wrong. Those are correct at that point, so it's at that point that I started to copy the wrong data. Let's run our test. And this is one of the dangers when you're working on such a large piece of code that's quite repetitive in terms of the coding, is that you can start making quite basic mistakes, which is why this large now and expanding set of unit tests is really supportive. Really, why I don't think you could undertake this project without having a good set of unit tests. Because even the unit tests can be wrong, as we just found out. Okay. So we want to do where are we? This is a very long class now, so it's going to have to be split up. So I'm already using partial classes to kind of reduce the amount of file space I have to kind of scroll through, but we're going to have to do something about the actual size of this class as well. And that's all part of the refactoring, and that's, once again, we've got those that large set of unit tests, so when we can refactor with confidence. In fact, we can almost certainly break the system, and it'll be quite easy to get back into a working state, because when our test passed, then we know we kind of got back into that state, which is very supportive. Okay, so this is a shift right logical set of flags, isn't it? So we can extract this out. We extract this in exactly the same way. Screwdriver extract method, set shift right logical. Shift right logical flags. Once again, we'll grab this. We're going to rename that previous one as well. Pop that there, and we'll say this is going to be, we're going to rename this the shift left arithmetic, just in case the flags are going to be different for a shift left logical. Okay, so we've got that. Right. So for so I wonder, we've probably got enough. Let's do shift right logical of HL, because that gives us a kind of a nice block of commands in the CB command table that's done. Do that one, and then we'll write some assembly language. Okay. For this one, this is going to fit into that gap we left. This is going to be 3E, and it's going to be basic similar to that one here, isn't it? So let's just copy that down. So this is 3E. It's shift right logical HL. Exactly the same as that. Shift right logical, and we better just check up on the timings for it. Where are we? Here. The timings are 4, 4, 4 and 3. 4, 4, 4 and 3, so that's okay. And we've got a shift right logical of HL there. So let's go and write a test. And what we'll do is no, what we'll do is grab this one here. Okay, so this is up to point to when we're doing an SRL. So this is going to be 3E, and we're doing an S shift right logical, and we're going to have the same piece of data there pointing to HL. Okay, so we're going to shift this value to the right. So the value is 0, 1, 0. This. We've got 0, 1, 1. We're going to push the 0 in from this end. We're going to take that into the carry flag. It's going to be 1. So we're going to have 0, 0, 1, 0, 1, 1, 0, 0 as our result. 0, 0, 1, 0, 1, 1, 0. So in the location pointed to by HL, after a logical shift right, 0, 0, 1, 0, 1, 1, 0, 0, 1, 2, 3, 4. That's going to be our result. The carry flag, we had a 1 that dropped into the carry flag, so the carry flag should be set. We said that the sign flag would be always unset. That's false. The Z flag, it's not 0. The half carry flag was always going to be false. Parity. So the parity is still odd, so that should be false. Because we only got 3 1s. N will always be false, and then we've got our undocumented sign bit, undocumented bits, not sign bits. So let's have a look at those. So 0, 1, 2, 3. So 3 and 5 will be set. So both our undocumented flags should. So that's our expectation. Obviously, if we run that, nothing's going to happen. It's going to fail. So 44 is expected. We got 89. Okay, so we should be able to write this fairly quickly now. So we're going to read value at HL. We've got our fetch 1, and we pass in the CB instruction table, and because we've got an addressing mode set of register index by HL, we'll get that value. So we've got that, and then basically we can pretty much have this code above. So we do exactly what we do before. We look at the bit 0 to see what's going to go in the carry flag, so the carry flag accordingly. We've got our shift right logical flags, and here this is going to be a write to bus, and we're going to write to HL, we're going to write the value N. Okay, so let's run our test again. We're failing here. So this is failing on the carry flag, which I've set to false, and actually it should be set to true, because we did carry a 1 off the end here into the carry flag. So that's correct. So I need to change this comment. Flag is set. Okay, so we've got that done. That's shift right logical HL. So we've got enough bits and pieces here to actually write a meaningful piece of assembly language. So let's first commit these changes. So we wrote shift left arithmetic, and we added shift left arithmetic R, shift left arithmetic HL, shift right logical R, and shift right logical HL. I'll just write those down as well. Let's commit those changes. Okay, at this stage I'm just going to take a very short break while I go and refill my my cup here. So be with you in just a few seconds. Alright, we're back. Thank you for waiting. Well, just in case you weren't here on the earliest part of the stream, this arrived today. This is building a Saturn V Lego model, and we're going to be doing that on stream. I hope to start on a Wednesday. So we're going to build stage 1 and really kind of up the rocket nerdetry a bit on the stream. Okay, so what kind of program can we write with what we got so far? Well, I mentioned earlier that the new Z80 enhanced that's going to be in the ZX Spectrum next has got a multiplication command, multiplication opcode. Our Z80 doesn't have one, so let's write an assembly language program to multiply two 8-bit numbers together and see what that looks like. So let's go back to the whiteboard. Let's kind of have a think about what multiplication actually is. We'll use base 10 to start with, then we'll go to multiply some. We'll go and multiply some numbers together in binary. Let's go back to our coding view. So here we are in the whiteboard again. So let's think if we have something like church numerals. So if we have 42 times 21. So the way we can think about doing this, if we kind of think of an algorithm that kind of does this, we take this digit here and multiply this whole top number by that digit and we get 42. Okay, and then we can take this digit and we can multiply that top number by 2 and we get 84, but we shift it across to the left, so it becomes 840, and so the total is 882. That's our multiplication. We've done some addition there. So our CPU can do addition, okay. Our CPU can shift to the left. We've just written those commands that do those. So that's how we do base 10. Let's have a look at a base 2. Let's think about that. So if we think about 1010, let's say, and we multiply that by 0011, what we're going to get, well, this number here is a 3, of course, and the top number is 2 plus 4 is 6. Sorry, it's 10. 1, 2 and 8. So we're going to expect to get 30, aren't we? So let's have a look at what we do. If we take this digit here and multiply the top one by it, we get 1010. Now the next digit we're going to multiply by this. We're going to get 1010 because we've shifted it across, haven't we, to the left. So what we get, the result of that, if we add those together, obviously 0 times all that and 0 times that is 0. Add these together, 0, 1, 1, 1. So that's 2, 4, an 8 and a 16 equals 30. So we've multiplied two binary numbers together using this concept of you multiply by each digit of your multiplier. If this is the multiplicand, this is the multiplier, then we are basically what we're doing is we're taking each digit of the multiplier, multiplying by the multiplying the multiplicand by that, and as we move through the digits here, we are shifting the results and then doing an addition. So that seems like a reasonable basis for a program, an algorithm which we could use. Let's think of just drawing that out. This might be a bit of a train wreck. I'll try to draw this. So we're going to start. As with most programs, we're going to do some kind of initialization where we set up our data. So for your stable, when you consider the work done by multiplication is pretty cool, that's when a CPU today can multiply two floating numbers together per clock cycle. Absolutely. You have 4 cores, it can do 64 multiplications per clock cycle, and that's at what, 4 gigahertz. So yeah. But when we're back in 8-bit days, in 8-bit CPUs, oftentimes if you knew what one of the numbers you want to multiply by, they would actually build lookup table, because it was quicker than doing what we're about to do. So yeah, it's amazing what can happen now, and it's going to be more amazing in the future, isn't it? If the doubling of computing power does actually continue. Yeah, it can be incredible. So what we're going to do then, we're going to have a look at, I'm probably going to run out of space on this, but we're going to have a look at the lowest significant bit of the multiplier, and we're going to say, is that 1? Because if it is a 1, then obviously we're going to be able to do our little trick of writing down the 1 times the binary number, and then continuing with our addition. Okay, so if that is a 1, then the result is equal to result plus, I'm going to call it M is the multiplicand. Okay. And then what we're going to do is we're going to left shift the multiplicand. The M is the multiplicand, that's the top number, and here we're dealing with the multiplier. Okay. If that was a 0, then we actually want to just skip around that whole thing. Okay, and then we want to look on the next least significant bit. We use this flowchart, but there we go. Now, how many bits are we going to look at? Have we done 8 bits? If it's a no, and we want to go back into here. This is a yes, no. This is a yes. We end. I do appreciate that's a really, really rubbish flowchart. But basically what we're going to do, we're going to set up our variables. We're going to look at the least significant bit of the multiplier. Is it's a 1? Then we're going to add the multiplicand to the result. Then we're going to left shift the multiplicand and carry on with that loop till we've done it 8 times. Okay. So, what does that actually look like in code? Let's go and write some code. What we're going to do is we're going to write the code in a on an assembler. So let's go and see if I can find where I. Yep, here we are on assemblers here. Okay, so Copper Beardy, welcome to the stream. Good to see you. So yes, fuel stable. So the lookup table thing is now a harmful thing, but it was then back in those days. I guess it was easier to do. You could do it in less bytes. So that's why they used to do it. So we need an origin for our program. I believe we can set this. We'll set it to 8,000. We'll do that with 8 in hex. 8,000 hex. That's the origin of our program. So we're going to start at 8,000. It doesn't really matter where we start, but okay. So what's the best way of doing this? So we're going to load register pair BC, and there's a reason why we're using a register pair with a value, and that's what should we multiply? Let's multiply that 42 and 21. So this is going to be our multiplier. Our multiplier is going to be 21 decimal. Into the top of that register, which is register B, we're going to load the number of bits in a byte. Okay, so that's B is going to be 8, isn't it? Now what we're going to do here, I think I'm going to. I don't know if I can. Will not let me indent them, so it's not going to look very pretty, but we'll see. Okay, so we're going to put our multiplicand into register pair DE. Our multiplicand was 42 decimal. Okay, I don't know if you can see. Actually, this is very small, isn't it? Let me see if we can zoom in a bit. What's the best way of zooming in? Zoom, there we go. That should be better. Okay, and we only want number 42. We're only dealing with 8-bit multiplication. 16-bit is a bit more involved, but we'll come to that at a point in the future perhaps. We want to load the top of that register D with the value 0. So it's 40. So we're basically using E, but we're using this register pair, and we're using that because we want to do 16-bit additions because the result could be 16 bits. Is why we're having to kind of fiddle with these registers. This is all part of your setup, and we're going to store the 16-bit result of our multiplication in HL, but we need to zeroize that to begin with as well. So now we've done our kind of init part. So in assembly language, we can actually have labels. We're going to create a label, and the label is going to be multiply. So colon means this is a label. This is going to be a memory location, and in here we are going to shift the. So what we're going to do, we need to know what the value of bit 0 is in each case, because we're going to be shifting that. We're going to be shifting the multiplier around, aren't we? We're going to move it around. We need to know what that in our flowchart here. We're always looking at the lowest significant bit. Okay, so we want to know what the lowest significant bit is each time. So we're going to do. We're going to copy that least significant bit into the carry flag, and we just learned how to do that with a shift right logical. You'll remember that we shift it over, and whatever's in bit 0 ends up in the carry flag, and then we can test it. Is it a 0 or 1? Remember, we can only test flags. There is a way of testing each individual bit, but it's not going to be very easy to use because you have to test a particular bit each time. So we do a shift right logical of C. Remember, C is our multiplier. So now this is going to say, we have a comment least significant bit in carry flag. Right. So what we want to say is that if it's 0, we want to do that branch. If it's a 0, then we're gonna skip around this addition part. Okay. So we can do a test. We did some tests before. I'm gonna jump relative. Jump relative. No carry. 2. No add. And we're going to define no add in a second. Otherwise, we're going to add HL and DE together. Remember, DE's got 0 in it, and D will have 0. E's got 42 in it currently, so we can add 42 in there. So it should be 1 times 42 at this case, because we've got a 1 here and a 42. Okay, then we've got no add. I can't quite see. And this is going to be where we're going to shift left arithmetic the value in E. So we're going to move it across. So now, rather than 42, it's actually 420. We're going to have 2 lots of those if we're working in kind of the equivalent of decimal. Now we need to save the leftmost bit into D, so we can rotate. In the highest bit, rotate left into D. So that's going to save that bit. And then we want to decrement B. And then we want to jump. If B is not 0, back to multi. And at the end of that stage, if we drop out the bottom of there, then HL should contain our result. So let's see if that assembles. Parameters needed, line 12. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ah, okay, deck B. There we go. Assemble. Okay, so we're assembled. Let's have a look what's happened to that. It says find at line 7, used at line 13. Yes, that's correct. Defined then. So we've got a program. Let's copy that. Okay, probably have to come back to that actually. Let's go over to our tests. So we've got a set of tests over here called Z80 Emulator should, and this is a way of loading an Intel hex file. So we're going to load that that program in. So let's copy this test structure. So we're going to execute a multiplier multiplication routine. 8-bit multiplication routine. Just a routine. Okay, so let's copy in our program. So we got the actual program written down. So it's over here. Copy that. We had to add in all 8,000, didn't we? There. Jasika, thank you very much for the follow. Have some hype. Electric Elf hype, courtesy of yours, Nabel. So this is one of the shaders that he's done for the stream. We've also done a number of joint streams on the whole subject of pixel shaders. They're all up on YouTube, on my YouTube channel. Which I'll post up in chat for you. Please do pop over there and subscribe. It's completely free to do so. We're chasing 150 subscriptions over on that channel at the moment, so I'm really be grateful if you are interested in what I do. All my streams, all 70 of them, are all archived up there, and this one will be up tomorrow. Okay, so there's our program. Now what we'll do is just tidy it up a bit. To be nice. Oh well, I don't think it's going to play nice with me, but I'll tidy it up later. Oh, there we are. It's a bit better. It's probably I'm a bit kind of OCD about that kind of things lining up. Okay, so there's our program. So we can then debug it if we get it wrong. So we're going to load in a multiplier hex file. We're going to set our program counter to 8,000. How many commands are there? There's 1, 2, 3, 4, 5, 6. We don't know how long that's going to take, do we really? That's kind of one of the problems. It's going to go round 8 times. So we'll just have to figure that one out. We don't want to like that. What's the best thing to do in terms of actually running that to completion? What's the best thing to do? Perhaps the best thing to do is to say no. I'll figure it out in a minute. Okay. Is the best thing to do just to write this into okay, we'll do it this way. So okay, so we loaded BC with 21, D with 42. We want H and L is going to have a result in it. Okay, so H, L, CPU. Ahmed Sar, thank you for the subscription. Thank you so much. That's very, very kind of you. Have some hyperspatial hype. This is another shader based upon a fractal. This is millions and millions of our alien buddy Alf. You now have access to the Alf icon, the emote, so the hype one. So this one you've got now access to. So welcome to Codebase Alpha as a astronaut. So warm welcome. Okay. So let's work out what the result should be. Get our programmer's calculator, working decimal, so we've got 42 times 21 is going to be 0372. It's going to end up in HL, and we don't need that, and we don't need that because we're only going to be operating within registers. Okay. So let's go over to our online assembler. So here we have the hex file output. So this is an Intel hex file format. And is it going to let me copy that? How interesting. Why wouldn't it let me copy it? I thought it would. There we go. Okay, so let's go to our hex files and we'll create, this is multiplier.hex. Add a file into there. File. Multiplier.hex. Is it called multiplier? Multiplication. Hex. Put that file in there. Is multiplication. Okay. So we should now be able to go into there and actually step through the program. What we're going to need to be careful of here is we need to go because we only got single stepping at the moment in the CPU. We need to actually perform the correct number of steps in order to run this program to completion. But we need a way of doing that really. So we'll use the program counter to do it. So this is 8017 there, 8017, 8018, 8019. So when the program counter gets greater than 8019, then we've finished the program. So, so what we can say is, and this may or may not work so easily. So we can say while CPU.program counter is less than 0x 8020, then we're going to step. And then we're going to pop a breakpoint here. And we're going to execute our test, and it's almost certain to fail because that's the way things are going to go for us, but we'll work it out. Okay, let's run this one test. Oh, we didn't debug it. Debug. Okay, so 882 has appeared in. Well, that's correct, isn't it? So that's, if we take over here, we say 42 times 21 is equal to 882. So it's actually worked. So our program worked, which is pretty nice because that means that we've now written a very, very basic multiplication program in assembly language and run it on our emulator. So I think that counts for a bit of electric alpha as well. So I'm quite pleased with that. And we'll salute the code. So I think that's pretty much a result for me. I'm pretty happy with that. Now, if we look at this code, there are things that we'd like to do to it to make it better. One thing that jumps out to me immediately is are these two lines here. Decrement B, and then jump if B is non-zero to multi. There's actually a command for the Z80, and it's why I chose to decrement B, so we could do this little trick, called DJNZ, which actually is one of these automated commands. It'll actually decrement B and jump if B is not zero. So let's have a look actually replacing this here. We've got like 1, 2, 3, 4 bytes. Let's replace it with something which maybe take up less space than 4 bytes. And you know, as I said before, when we're kind of talking about assembly language programming, we're talking about scrimping and saving on all those bytes. We want as few bytes as possible to do the program, and we want to choose commands which are commands which take up the fewest clock cycles. And yes, Fuel Stable, you're absolutely right. This is why looping towards 0 is better than looping towards a value, because if you're looping towards 0, you're checking a register flag, 0 flag to be set. But if you're looping towards a target number, Link Slumps, welcome to the stream, good to see you again. If you're looping towards a target number, you're actually having to do a compare and then see if that comparison was 0. So you're actually saving quite a lot of kind of clock cycles by looping towards 0. So Fuel Stable was absolutely right, and you know, it's now obvious why that is the correct thing. I mean, modern programming languages and modern computers, you know, maybe you know, if you're writing the ultimate performant program, you take that kind of into account when you're writing your C#. But you know, people don't do it anymore. When we're at this kind of assembly language level, machine code, then we have to take all this into account, because if we were looping up towards 8 rather than decrementing down from 8, we'd have to compare a number, and that's going to take us time, and also we're shifting data around inside that CPU unnecessarily. So we've got a little kind of optimization we can try and do to save a couple of bytes here. So let's have a go at that. So let's go and have a look at the user manual. Oh, by the way, if you wanted to check out this online assembler, the reason why I'm using this rather than using the WinApe Amstrad emulator I've got as well, is that I can just grab the hex file format here, and I've got a hex file reader in my code. So over here, you can see under classes we've got a hex file reader. So this is what is basically reading our the Intel hex file format. There's a bit to do, but I've not seen examples of these record types yet, so I don't know what to do with them. But this seems to cover everything I need to do. Yep. Okay. But all this is up on GitHub. If you want to take a look at it, so I'll just pop my GitHub into chat for you. So Link Slumps, Good to see you. Say kind of off topic. When is front-end frameworks like Angular a good idea versus a bad idea? Someone pointed out to you that if you want to do a lot of SEO-based stuff, it's better not to use it. Single-page applications tend to use a lot of those frameworks, like Vue and Angular, don't they? I've not worked with them much myself. My main exposure to Vue has been through experimenting with it, having seen Dev Chatter use it in one of his front ends. He mixed it in with Razor, which is very interesting. But yeah, I've got people at work who rave about Angular. I'm more cautious about things like that because of the speed of change of it. It seems to be kind of evolving so rapidly that you're always kind of behind the curve. But everything has its place, you know. So I don't guess I can really kind of advise you on when you shouldn't use it. Maybe somebody else in chat could advise. I suspect Fuel Stable would have some advice on front-end frameworks. I mean, frameworks are fantastic to kind of to speed your development along, and to use kind of particular models for development. Whether they're most optimal, it depends on what you're trying to do. But I don't know about the search engine optimization thing, I must admit. So yeah, I think it's a good idea if I think it's a good idea if you need kind of rapid generation of your for prototyping, for rapid generation of your application, especially for spas. So Copperbeardy, 11,552 words later, draft 1 of the dissertation is done. Is this for the OU, Copperbeardy, or was it for something else? And is it a computing-based dissertation? I know you did OU. I've done some OU as well. I really like the OU until they kind of started charging the earth. This is a master's with the University of Hertfordshire, and it is computer science. Excellent. So I really wish you all the best with that. Then, are you happy with your dissertation? What was the subject? If you don't mind me asking. The subject is the accuracy of Azure Map Services. Wow, that's certainly a master's dissertation, isn't it? I don't even know where to start with that one. That should be fascinating reading. I'm deep into Azure at the moment, and finding a number of frustrations with the way our architects, there's a third-party company, have basically locked it down to the nth degree. It caused me a lot of pain. But over the past 7 days, I've had to implement a caching layer into my services very, very quickly, and it was like a piece of cake to actually set up a Redis cache with Azure, and then go through the pain of obviously implement it in each of the methods. But I'm really impressed with some parts of Azure. But I think the way it's been architected for me in my company, it's a bit too locked down, especially for a development environment. So I think some PhDs on the level of books. Yeah, so it wasn't long enough perhaps for a PhD. So Copperbeardy, I really agree, because there's two things happening with the OU, and I don't want to diss the OU because I really, really enjoyed my time working with them on. I just chose the odd module and did that. I wasn't working towards a degree. I've already got a degree, so I didn't need a new degree. I just wanted to kind of. I'm not formally trained in computer science. I'm a chemist, so that's my degree was in chemistry. So I had no formal training in computer science, just knowledge of an interest built up from practice and as a young person playing around with Z80 processors and 6502 processors. So I used to kind of just pick a module. You pay your money. It'd be, I don't know, £400 or £500. You do 3 months, do your exam, and you get your points, and then you could take it or leave it, and then you would kind of come back a bit later and do another one, for example. When it moved, not only did it cost as much as going to university, pretty much, at least to one of the kind of less well-known universities, also a lot of their materials started going online. And the great thing about the OU was the quality of their written materials, which I thought was absolutely second to none as a teaching, a teaching and learning medium. The OU written material was fantastic, really, really, really brilliant. And so I think they're basically, not only they're charging an awful lot of money, but also everything now is online, and you get no permanent thing at the end of it, because once you finish your course, your access to the website goes away, and you don't have that legacy of those wonderful books that you've written in and coloured and highlighted. So online learning is not nearly as good as bricks and mortar, and I 100% agree. I think it's much more difficult. Why I admire anyone who got a degree from the OU. So my degree was with a red brick university, and I'm proud of my degree. But if somebody comes to me looking for a job and they've got an OU degree, it says an awful lot about them, because they did that while they were working. It took them a long time. Online stuff lets you dip into niche topics, but they're shallow. Yeah, you don't get the depth of teaching. Yeah. What am I trying to find? I'm trying to find decrement and jump not zero, and we can implement that. Let me see if we can find it. It's in the jump group, low group, jump. Yeah, they are DJ NZ. There we go. Okay. DJNZ. This is a 2-byte operation, and you can see that here, decrement B, and then jump non-zero to an address is 4 bytes. So now we're going to do that a lot quicker. Okay. So let's added multiplier, multiplication, program, test. Take that away. Okay. Let's go over to our instructions, and I need to find the jump group that we worked on last stream. That's 16-bit arithmetic. Here's the jump group. Okay, so let's. So this is going to be DJ and Z. So we're going to be. This is going to be decrement B and jump 0. Okay. Right, okay, so let's go and have a look at these. That's a bit more detail. So if B is non-zero, we're gonna do the old PC is PC plus E, which is the dual decrement thing that we did before. E is going to be in the range of minus 126 to plus 129 because of the dual decrement. So we should be able to just go and look at the jump relatives here. So if I grab this piece of code and just copy it down, we can use this as the basis. This is going to be decrement jump non-zero. So we're going to get our value of E, which is going to be our signed byte. So it's going to be a relative jump. So we're limited how far we can jump. We're going to check if the Z flag is 0 here. So what we need to do is decrement B, don't we? And then check if the result of that is not 0. Okay. So we have got a decrement. We've got dec R, haven't we, there? So is that the best way of doing it? Okay, so what we're going to do, we're going to go and look at what dec R does. Let's search for that. Dec R. So it sets the flags here. So we want to do that and that. Decrement flags, which is what we want to do. So we want to say decrement B, back where we came from. Yeah, so we want to decrement B, so B minus minus, and then we want to do set dec flags, and we want to pass in the new value of B, and then so that should okay. So what's it saying? So it's going to be val and dec val. The original value. Okay. The value before and then the value afterwards. I'm going to say initial value is going to be B, and we're going to pass in initial value and B, set the decrement flags, and then we're going to check the flag, Z flag. If that is not 0, then we're going to do a relative jump by altering the program counter by the value E, which is a positive or negative value, and then this mem pointer thing here is an undocumented feature thing. So we are saving away the value, the place where the program counter where we're going to jump to. And that's important for a number of undocumented features, which I'm not going to go into at this stage. So let's go on with chat. So it takes a lot of self-discipline and organisation to study remotely. This copyability, absolutely true. The Masters wrote not different. It's all 95% self-guided. Well, yeah, and a Masters would be anyway, wouldn't it? But I can appreciate the effort of having to hold down the job as well to do it. If you want a brain burner on a niche topic, purely functional data structures. Not data structures or Lisp. Data structures, but immutable ones, yeah. I think I've got an awful lot to learn about the power of having immutable data. Seems like it seems like a hindrance to begin with, but the more you kind of work on it, the more obvious it becomes is your data should be immutable. Okay, so that's that. So we need a test, don't we, to work on that. So let's go to our jump. Let's go to our jump group test. So what have we got here? So take this test. So we're going to jump forward. Well, we're going to jump back, aren't we? Jump back for decrement jump non-zero. When non-zero. Makes sense? Okay, so we need to set up our, before we can come back and do the rest of this, we need to set up our command. So let's go and find decrement jump non-zero in our opcodes. There it is. Decrement jump non-zero n or 10. Just make sure with our user manual, yeah, 10. Okay. So over on our Z80 root instruction table, we can now insert 10. Okay, so let's do that. So 1x10, the new instruction. This is going to be have a mnemonic of DJNZE. It's going to have immediate addressing, immediate extended. We only got one reason to address, so its next one's implied, and it's going to be GJNZ as our function, and then we've got a new list of integers for our timing. And what's the timing on that operation? So the timing is 5, 3 and 5. Oh, it's different, look, it varies. So this is an interesting one. It's non-zero, it's 5, 3 and 5. It is 0, it's 5 and 3. Now that is interesting. Okay, so what we're going to do, okay, so we're going to say it's 5 and 3, and then we're going to alter it by 5. So my idea is we say it's 5 and 3. Now, and what we're going to do is over in instructions we're going to say additional 5 t-states. What to do on that, and we'll address that at some point in the future. You like immutable topology, but that's what I think I was saying for your stable. And the data's got to change, obviously, but the data structure that it lives in, it should, yeah. Yeah, and this is where I hit a terminology barrier, I think, with a lot of this stuff. Sure, now when you talk about immutable structures, and then you start talking about lenses, and I know that Gareth Hubble did some work with lenses, and it was just maybe if I was kind of steeped in that terminology, I'd kind of get it, but I struggled at that point because of the terminology being used. They're talking about these lenses and what exactly you're talking about. Now, I think it's relatively simple, but that was the barrier, and I kind of lost the thread of what was going on at that point with when Gareth was working on them. So it'd be really good to to understand that kind of thing. It might be a subject for a stream in the future, a joint stream, I think. Yeah, I'm sure it's quite simple. Your step, I'm sure it is. But I do find some of it's like reducers. people talk about map producers, and I think it's all simple, but I wonder why they. Yeah, we could talk about the stream. Yeah, I think it's maybe not as a whole stream, but as a kind of maybe a backwards and forth chat about that kind of thing might be quite a good concept. Okay, so we need an additional 5 T states at that point. Okay, so that's the first time we come across a command or an opcode which has a variable number of machine cycles or T states involved. So that's interesting. Right, so we've got, it was 1 0, wasn't it? So jump cut. So it's going to be 1 0, and it's going to go back. We're going to go back. So we want to go back. What did I say? 4. FF, FE, FD, FC. FC is -4. So this is decrement jump, not 0. We're going to go -4. Assembly will compensate, and what we're going to do is have some code. We're going to have some memory locations before. So this is going to be 7F, 7E, B, C, and we're going to jump here. Okay, so I got that. So we need to set our B register up, and the B is going to contain F. So the program counter should actually get changed to 7C in this case. So what's going to happen? Let's run our tests and find out. So what actually happened? So it's ended up here because it's jumped back. Okay, so that's right. So in fact, when we say 4, what we actually mean, when we say 4, it would actually it would compensate automatically. So when we say 4, this has got to be, it would actually put FA in there, and we can prove that. We can prove that. So let's do that. Let's bring up Win8. So this is an emulator which we can use just to prove that. So we're going to have origin 8000, and then we're going to say load B with 5 decimal, and then we're going to do a decrement jump non-zero, $-4. We're going to go back 4. In fact, let's start this there, and then we're going to have a NOP and a NOP. Let's see if that will assemble. Jump out of range. Okay. Bunch of NOPs. Assemble that. That's going to be hexadecimal, so let's pull that. Okay, so that's assembled. Oh, that's still saying code expected. that? Can't remember. That's better. If we look at what it's actually produced, you can see that we said -4 here. You can see it has put FA, so the assembler's compensated for that. The fact that the program counter got incremented twice as it read the instruction and then read the assigned byte offset. So we're correct. It should be FA. Let's prove that. I hope you could see that. But, so this is what this kind of comment here means. The assembler will compensate. So we have to FA in there. So this should actually run now. And what's failed this time? Oh, it's checking the flags. Yeah, we don't want to check flags. We don't care about that. That flag's unchanged. And then we want to do the test again. And this is not jump. Not jump back 4 and 0. So this is going to be that, and then we're going to have B is going to be 1. This time the program counter should end up at 82, I believe. Is here. So that. Yeah, so okay. So that's all working. So that was kind of an example where we're doing kind of whether we're doing test-driven development. I've kind of gone off the rails a bit there and wrote the test afterwards, but that's okay. I'm not going to be a slave to it. Okay, so we've got that command in there now, and what we could do is we could go back to our online assembler, and here we can change this to that, and then we can get rid of this. Yeah, we can assemble that. Oops. It was relative jump now, isn't it? So we do that. We can. So now it's going to jump back to the multi, which is F5. So F5. So that's it's gone on to, yeah, that seems right. So let's try that. Here, Session Explorer, new file, multiplication 2x. Okay, that's that. And then we'll go to our emulator should. Copy it. Do routine multiplication 2, and instead here instead of doing do where's our assembler? That should be there. Oh, that's interesting. What's going on there? I'm just putting that backtick in there to try and make it disappear, so now we should be able to just go across. Oh. There we go. And that one there goes. We seem to do that. There we go. So now it's going to be, if it's less than, we save 2 bytes, so we can reduce the number of steps we do, and we should be able to run that. Multiplication 2, everything's set up exactly the same. Let's run and see what happens. Yeah, okay, so that's pretty good. So added DJ with usage a short program. Okay, I think that's probably as far as I want to go today. It's now what, 5 to 11, so pretty much time to call it a day. So let's have a look what we need to do. We need to now sync this up to GitHub. We're doing a reasonable amount of work today. We added quite a few interesting kind of shifts, arithmetic shifts and logical shifts left and right. We added a new jump command which is saved us a couple of bytes, and we've actually managed to write some assembly language programming which actually did a useful task of multiplying 2 8-bit numbers together, and we've actually tested it in our emulator, and in 2 different variants on it, it actually works. There's more we can do to optimize this program though. We're doing a lot of these shifts around here. We worked quite hard to actually get those shift commands into the emulator, but actually we're doing a lot of them. We're doing a right, a rotate left, a shift left arithmetic, and a shift right logical here. And in fact, we probably don't need to do all of those. We can save quite a bit of time in not doing all those shifts, and we can also simplify our initial setup of our registers, I think. So I'm going to work on that off stream and come back to you with an optimized, a more optimized program. Maybe look at doing a 16-bit multiplication as well. Okay, so let's sync this up to GitHub. So what I'll do is we'll test out a feature. Let's test something out. So I want to go over here. I'm going to post my GitHub into chat. Okay, and then we're going to do this. See if this will work. So I'm trying to use a feature called Featured Chat, and we'll see if we can get it to work. In fact, I'll drag it over so you can see it. So this is Featured Chat, and if I grab this and I add that on deck, we should see it appear there. So I don't think I've got the featured chat actually working on on this scene, but see, that's our GitHub repository. So I'm just showing that on stream so people can who watch the video can get that that link. Okay, so that didn't quite work out, but I'm sure it will do. Well, that's all. That code's all saved up there now. So let's go and have a look about who we can raid. Just a reminder. I'll just reach down here. On Wednesday, we're going to have. I'm planning on a stream which isn't programming, so it's going to be. We're going to be looking at this. So let's just put to our desk cam. We're going to be building a Saturn V Lego model. We're going to start off with stage 1, and we're going to build it live on stream. It should be a bit of a laugh, something a bit different from what I've done before. So yeah, if you're a rocket nerd like I am, join me for the construction of Saturn V. As you know, it's 50 years since the moon landing, the first moon landing, and so I've just received a copy in the post actually of Apollo 11, the film Apollo 11, the documentary. So I'm looking forward to that. I'm looking forward to doing this, and kind of honouring the people the men and women who made that Apollo program possible and put those men on the moon. So that'd be great. So let's go back over here. Okay, so let's try and find someone to raid, shall we? Okay, so Twitch. I wonder who's actually on at the moment. I'm going to have to shrink my browser down to a more normal size. So, let's have a look. Is anyone on tour? Oh, we've got Robert Tables, we've got Saw Scoop, Janiscu's on, so let's go, I don't know, should we do... Robert Tables has got a fair number of people, let's go and raid Saw Scoop, shall we? So let's go, I don't know, should we do... let's go over here. Oh, I've got some gifts here. I don't think anyone's in... A couple of people are still in chat. I'll distribute these gifts. I don't know exactly what they are. They're just free stuff if you're on, if you've got Twitch Prime. So those have gone out if people have if anyone's got Twitch Prime, they should receive something from that. Okay, so 227 followers. So thank you very much to those who've followed. That's really kind of, we're speeding on towards our 250 target now. Let's go and raid. So we're going to go and raid Saw Scoots. So do join me on Wednesday at about 4 o'clock in the afternoon UK time, that's UTC, to build stage 1 of a Saturn V moon rocket out of Lego. I think it should be a bit different, and I'm quite looking forward to it. So I'll see you then. So take care everyone, and let's raid. Do stay in chat if you want to join the raid. And if you do, spam those emotes. Take care.